Log on, tune in, find out. Another good idea from Cambridge.
It's a pleasure to have Olaf Hohm from Munich.
That's right.
Who's going to talk to us about the geometry of non-geometric fluxes.
Thank you very much. Thank you very much for the opportunity. So I'm going to talk about non-geometric fluxes and at least some version of non-geometric fluxes and how to write down actions for them. So this is based on this recent paper, which is actually just a short letter, so a longer one with all the technical nasty details will appear soon, I hope. And that's work done in collaboration with David Andriot, Magdalena Laforce, Dieter Lüst and Peter Patalon, all people from Munich. And I think Magdalena talked already here at some point about some earlier work they did last year, and this stuff completes it to some extent. So let me just start with the motivation, non-geometric fluxes. So the motivation is as follows. So is that readable from the last lines? Very good. So we consider compactifications, in general flux compactifications, of string theory, or to be more concrete, let's say 10-dimensional supergravity. And as usual, that gives rise to supergravities in lower dimensions, let's say in 4 dimensions. And if you do flux compactifications, it gives rise to so-called gauged supergravities. So gauged supergravity means that there's a certain local symmetry. And these are interesting for phenomenological reasons. You have non-trivial potentials, and you can look for de Sitter vacuum and things like that. So I won't say too much about this in detail, but just to be a little more specific, let's look to the standard action, the minimal action of, let's say, bosonic string theory or the NS part of superstring theory. So we just have the standard action for a dilaton metric and 2 form. So we have the Einstein-Hilbert term, dilaton kinetic term, and an h squared, where h is dB, b is the NS2 form. So that action is the one we will be considering, and it's double field theory extension at some point. So as I said here, Hij is just the field strength of the B field 2 form Bij. So IJK are space-time indices. And now you can give, for instance, a VEF to the 3 form. So you can have a 3 form VEF. It's very noisy, I'm sorry. For the compactification. And that gives rise to gauged supergravity. So that's one example. But the basic observation is, there are many more gauged supergravities in lower dimensions than what you can get naively from flux compactifications. So there are more gauged supergravities in 4D, let's say, but also in most other lower dimensions. So the question arises, what happens with those gauged supergravities? So with many more, I mean that if you just analyze the supersymmetry in lower dimensions, what can you consistently write down? That they are more or less all classified, and in particular they come in T-duality complete multiplets, and you see only a tiny or a smaller subclass appearing through compactification or flux compactification. And that has led to the proposal of non-geometric fluxes. So here we give a flux to the 3 form, for instance. But the idea is that you should also consider something that is called non-geometric fluxes. So that goes beyond these standard 3 form fluxes. And these non-geometric fluxes are supposed to be related via T-duality to the standard ones. And the chain that is almost given in any single paper on the subject is as follows. So if we start just from the standard three-form field strength of this NS-NS action, let's call it HABC, we can consider a chain of T-duality transformations. So that I won't explain this in detail, just for the motivation. So you can apply several T-duality transformations to obtain objects with different index structures. So T-duality naturally switches indices, and so you get an object with an index up, Fa, then you do it again, you get an object which is usually called Q, 2 indices up, and then in the last step you get an object with 3 indices up. And as I said, the H is just the standard usual 3-form. Now T-duality links the B field to the metric, so this F is basically what is sometimes called the coefficients of anholonomy. So it's this combination. If you're in a Vielbein or frame language, it is essentially this object. And so that's sometimes called geometric flux, but you know it's just related to the standard Levi-Civita spin connection. Well, up to a linear combination of these guys gives you just the standard spin connection. So that's related to the connection. But now the question is, what happens to these two guys? Is there a geometrical interpretation of Q and R? And yeah.
H is a tensor, right? And then F, if it's really the connection,
is not a tensor.
not a tensor.
It's not a tensor, and that's exactly a crucial point. I will discuss this further, so I can give you already the punchline if you want. So the Q will also turn out not to be a tensor, but the R is a tensor again, but in a generalized sense. Thanks for that question. So coming back to our standard action, so we have an action here which involves the H squared, the usual 3-form field strength, and of course it also involves the connection inside the R. The Einstein-Hilbert term involves the, depending how you write it, the spin connection or the Christoffel symbols. And now the question is, can you write on a similar action which has instead of this, or in addition if you wish, a Q and an R term? And that will be what I'm trying to do. So before I get into the details, let me give you a schematic diagram of what we have been doing. So starting from 10-dimensional supergravity, we can of course, standard 10D supergravity, we can do a flux compactification or any compactification. And what we get is, let's say in 4 dimensions, it doesn't really matter, 4-dimensional gauge supergravity. Now, gauge supergravities in all dimensions can be classified, and this has been done by means of the so-called embedding tensor formalism. That's just one way, but it's one way which is particularly convenient, especially in this context. So for those of you who have never heard of it, the embedding tensor formalism is just parameterizes all gaugings in terms of a tensor, usually called theta, that tells you how the gauge vectors couple to the various fields, and it determines the scalar potential, etc. But the crucial thing is that this tensor is a tensor under the duality group of whatever theory you're considering, and these duality groups usually contain the T-duality group. And another issue is that the gauge supergravities can be written in a fully T-duality covariant, or more generally duality covariant way, where the embedding tensor enters as a covariant tensor. So that means that you can apply now to a given gauge supergravity some sort of T-duality transformation. For instance, I put it in quotation mark because in this context maybe it's not really a T-duality. So let's say take a group element in O, let's say 6,6. So we know the T-duality group is usually ODD. And this is typically part of the duality group. So you can apply it, you get a different or a new 4-dimensional gauged supergravity given by this new transformed embedding tensor. Let's call it theta tilde, which I mean just the action of this group element on this covariant tensor. Because everything is done in a covariant way, this is not really a totally new theory, because you can redo a field redefinition taking the form of this T-duality rotation to undo it. But in any case, through the standard flux compactification, we don't get T-duality complete gauge supergravities in lower dimensions. Rather, we get only particular cases. And one of the questions you can ask is, what should I do to get already from the higher dimensional point of view, T-duality complete multiplets, if you like, of gauge supergravities? And I think that's one way of presenting this work, which my collaborator have started last year, is that what they did, they started in 10-dimensional supergravity before any reduction, and have rewritten it in new variables. So have performed a T-duality, not a T-duality, have performed a field redefinition that takes the form of a T-duality transformation, the same way as you can do it in the lower dimensional theory. So they performed a T-duality inspired, if you wish, field redefinition to obtain a new 10-dimensional supergravity theory. Let's call it tilde. And then the idea should be that if you start from this one and do a conventional flux compactification, you get this new T-duality transformed gauge supergravity. Now this step here, this field redefinition, was extremely involved in their case, and they also didn't really do it well, because of the technical issues. It was very difficult to do it completely, so it was not quite done completely. And so this is now about completing it, but also understanding this in a wider context, because we will understand this in the context of something that is called double field theory. And since double field theory, as I will briefly review in a moment, is formulated in a way that makes T-duality manifest, it contains, if you wish, already both versions in a universal formulation, and in this formulation it just amounts to choosing different parametrizations. So maybe some of these steps are still a little mysterious, but just as a general outline of what I'm trying to do here. So let me start now by reviewing this field redefinition I mentioned here. So in 10 dimensions we can do this field redefinition, and this field redefinition takes the following form. So in order to characterize it, we write down an object H, which is called the generalized metric. So this H is called generalized metric. And these indices Mn are indices running from 1 to 2D. So they are actually indices under ODD, and you can think of D being 10. I will always switch between D and D is 10. And this generalized metric is defined, or is usually written, as a particular combination of the standard metric and the B field. So you have Gij minus Bik, Gkl, Blj, Bik. So it's a nonlinear combination of the standard metric and B field that is done in such a way that T-duality acts linearly on this object. So that's just a particular combination of G and B. And what they did is they rewrote, my collaborators, they did a field redefinition, which you can basically characterize by saying that this matrix H, written in the standard way, is equal to a new one in terms of new variables. So you introduce a new metric, G tilde Ij, which is just this particular combination here. So metric and B field mix now in this field redefinition. And you have the following components. Now you have a G tilde And you see now you have a beta instead of a b with upper indices. So it's still an antisymmetric tensor, but it has upper rather than lower indices. And that will play a role in a moment. So if you just look into it, we just swap rows and columns, and we swapped indices for every single entry. So a G becomes a G tilde, a B becomes a beta with upper indices, and that equation here characterizes the field redefinition. So we go from old variables G and B to new variables G tilde and beta. And
one question, is it clear that that combination of the upper matrix in the total corner is invertible?
you mean the H?
Well,
The H is invertible?
well, I guess if you write G tilde is G minus.
Oh, I see. So you say if you you wondering whether this combination, which I call here G tilde, is actually invertible.
Yeah.
That's a good point. Actually, I think it's not clear. So that's a good point. That's actually so I haven't explained double field theory yet, but that's actually an issue in double field theory. So we have this HMN, and we usually write in terms of G and B. And now you can define the act as a T-duality transformation, and you could say, well, now I read off G and B, the new G and B after the T-duality transformation. But if you assume G to have Lorentzian signature, then it can happen that the G that you would read off becomes singular. But the point is that the H itself, the generalized metric, does not become singular. It remains regular, and that really tells you that H is the fundamental object, not the various components. But I will ignore this issue for the purposes of this talk. So that's part of the field redefinition, and another part is that we introduce a new dilaton phi tilde by this equation here. This looks also very familiar. Okay, so the upshot is that we get a new metric G tilde ij, and the interesting thing is now we get a bivector beta ij, an antisymmetric tensor with two upper indices. And so what my friends computed after huge heroic computation is that if you start from this action, do this highly nonlinear complicated field redefinition and insert everything, which is a huge mess, you get a new action in terms of G tilde, beta, and phi tilde, which is just as follows. You have a 10-dimensional action. You have e to the minus 2 phi tilde in front. And now you get the Einstein-Hilbert term still, but now with respect to G tilde rather than G. You get a kinetic term for the dilaton, and you get a Q square term. And what I mean by Q square term is the following. So let me write out the matrix explicitly. Hope it's still readable. So we have an object Q now that has mixed indices, and that's exactly the index structure we actually wanted to get here. So the claim is that this should be related to this Q here in the chain, and this Q is defined Q, M, and P, one lower, two upper indices. It's just a partial derivative of beta. That's the definition. And what I forgot to say is that actually they've thrown away all kinds of terms. So there's plus a lot of terms which are all of the form that beta im dm x on something. So that was just a simplifying assumption they had to make, otherwise the computation would have become horrible. even more horrible than it was already. And that's not the result. You get a Q squared term rather than an H squared term. You get a bivector rather than a B field. And that's the action. Now, there's three things to be mentioned about it. First of all, in order to get this result, you have to do a huge heroic computation, because you see this field definition being highly nonlinear. You have to invert the new metric, assuming that it is invertible. You have to insert into the Christoffel symbols. You have to insert into the Einstein-Hilbert term. You have to collect everything. It's a huge mess and it's a huge computation. And many terms they have ignored of this structure, therefore. So the question is, one of the questions is now, can I do better? Can I relax the constraint? That's one issue. A second issue is that the geometric role of this Q is rather obscure. So here we have a bivector. So we have an object with two upper indices, and we take the partial derivative of it. So that's clearly not a tensor. Now for the B field and differential forms, we know, of course, what's happening is you have a differential form. You can take the exterior derivative. That gives you a field strength, which is also a tensor. So you can write on invariant action. Everything is fine. Now for the Q, it's not so clear what you should do. You have this partial derivative. Of course, you can eventually covariantize it using the Levi-Civita connection, but that we found is actually not what's going to happen. So the question now is, what's the full action? What's the role of this Q squared term? And the final question is, what happens to the R? So far, we don't see any R.
How about the gauge symmetries? I mean, what is the gauge invariance of Q?
Yes, that's also not obscure in this formulation, but that's sort of less surprising, because doing this complicated field definition, the new objects we get now have a very, if you work it out, have a very complicated transformation behavior under what was originally the abelian gauge symmetry of the B field. So that is now obscured after all these field definitions. What should not be obscured, however, is the diffeomorphism symmetry, because we are still working with tensors, right? So G and beta should still transform in the usual way under diffeomorphisms. So the fact that this Q has this non-covariant form is a problem.
So I was worried about, ghosts and stuff like that.
Yeah. It's as I said, the gauge symmetry, what was originally the standard gauge symmetry for the B field is not manifest anymore. But since you've just done a field redefinition, there's nothing to worry about. It should still be, it's still around.
But somehow the linearized theory would be sick. You would have to work with a full nonlinear.
Yeah, well, if you just look to these few terms, you're right. That theory is sick, but it's not the complete thing yet. That will be the main of the purpose of this talk, to complete this.
So sorry, the stuff that you put in ellipsis, you're not ignoring it. You're saying you need that stuff to complete Q in a page.
My collaborators were ignoring it, but now I will complete this story. So that will be the rest of the
Using
talk.
precisely those bits that...
Yes, and actually even more, because I will do it in the full double field theory, and that was now the point I wanted to make. So all these issues become clear once we consider this in the context of double field theory. First, the computation, which was heroic, starting from the standard supergravity, becomes very, very easy in the context of double field theory, using that this field redefinition can be thought of as particular T-duality transformation.
Right, I've got to come back to the whole philosophy here. I mean, if you just start with something, whether it be supergravity or what, and do a whole bunch of field redefinitions and write down an action, don't I just go, so what? I mean,
well, yeah,
you've just done a field redefinition and written down an action. Where's the physics?
Yeah, no, I agree with you. You don't get new physics by doing a field redefinition.
But why do I even know to identify that Q with that Q? I mean, you've got here a Q to do a T-duality.
Yes.
You've then just done a field redefinition, which you've said I'll do a field redefinition, and then you've decided to identify the two things.
Yes.
Why?
Well, there's no official definition of Q in the literature everyone agrees on. So there's there's no rigorous proof you can do to say that Q is really the right Q. I mean, if you look to various papers on the subject, you find different proposals of the Q, and you can say that's one more proposal of the Q.
Don't say because people disagree, it's not defined. You've got a Q there on that board. You must mean something independent of that. So the Q you've got there, you've defined finding T-duality on F.
I haven't defined anything. That was just the motivation I copy from what
Can I ask
people
you to
tell me.
define what's on that board then?
No, I'm defining it here, what I mean by Q and R. That's all I'm going to do.
But 1 minute, if you're only defining it there, that's just from a field redefinition, then I'm worried.
What are you worried about?
Because you can always just do a field redefinition and define a Q. I mean, you were motivating this thing over here based on T-duality, and then it's,
well,
This Q is on a torus, right? And this Q is in flat 10-dimensional space so far, so they're really different. I mean, you haven't.
Yeah, you see, I mean, there are different ways to motivate Q. You can, what they originally did is you look to four-dimensional gauge supergravity, you look to the scalar potential, and you identify terms. You can go through the standard example of the torus, etc. And now, what we're doing here, I mean, this to introduce a bivector, which is associated to Q in a similar way, like the two forms related
what is
to
that Q? Because I just want something pinned down. Because what is that Q you've written there? You've got an arrow in its Q. What is it?
Well, do you see this question mark below it?
Well, up to Q, I guess it's two T-dualities, right? So if you think very naively in this Hall double curve ratio, you have a torus,
Sure, I do two
fiber, you can do two. The third one is the tough one.
That's right.
Yes.
But then, well,
Yeah, actually that's a good point, and I will come to this. The last T-duality you can only do in double field theory strictly, because there you have a framework to do a T-duality transformation without an isometry. So, may I continue?
You go to local coordinates where you have two kilometers. I think you can always do this. So the first two T-dualities
Yes, that's
are
right.
Busse rules.
but
That's
it's
right.
the fact that you then say it's in flux that you're writing in terms of some local potential.
Well, call it a proposal, and that's what it is. Well, that's what we are doing, and let me continue, please. So, as I said, this should be done in the context of double field theory. Now, I'm not going to review double field theory in all length, because I suppose there have been already a few talks on this subject, so just very few general remarks for those who never heard of it. So what we do is we double the coordinates in order to make ODD a manifest symmetry. So we introduce capital coordinates xm, m again running from 1 to 2d. The xi are the usual space-time coordinates, so I do it for the full space-time. And you can think of this x tilde as, in quotation marks, some sort of winding coordinates. And similarly, we have derivatives with respect to these extended coordinates. So we double the coordinates, but at the same time, because physically we know we don't live in 20 dimensions, we only have half of the coordinates, and this is implemented by a constraint, sometimes called the strong constraint, where you demand that the following is 0. So for any field or parameter A, dm dm, and by this construction I mean construction with the ODD invariant metric, we get 0. And here eta mn is the ODD invariant metric, which in the standard, the basis usually used, takes this off-diagonal form. And as well we impose that the following combination on products of fields or parameters is 0. And that constraint, you can prove, implies that everything depends only on half of the coordinates. So let me just write it also in components, because I will use that form in a second. So if I write the derivative with d tilde I di, this constraint implies reads as follows: d tilde I dia is 0, and d tilde ia dib plus dia d tilde ib is 0. So that's the constraint I have to put in order to reduce the number of degrees of freedom. And now there's a double field theory action, which is ODD invariant, manifestly ODD invariant, and it is written in terms of these objects H over here. So it's formulated in terms of HMN and the field D that is defined via this relation. So it's a particular combination of the standard dilaton and the metric. And so, as I said, the crucial properties of this action is it's manifestly ODD invariant. I'm not going to write it down because I don't use it explicitly here. Just to tell you, it's manifestly ODD invariant. And it has a gauge invariance with respect to a certain parameter, psi m. So it's a parameter that's an ODD vector index, and it has components psi tilde I, psi I. If you go to the d-dimensional indices. And now, just for completeness, the double field theory action, if you set now these extra derivatives to 0, so you set d tilde equal to 0, just reduces to the standard action dx root g e to the minus 2 phi r plus d phi squared, etc. So just the action we have over there. And in this case, the psi I gauge transformations just give you the standard diffeomorphisms. So the standard diffeomorphism xi goes to xi minus psi I of x. And the psi tilde I give B-field gauge transformations. So delta psi tilde dij is equal to di psi tilde j minus dj psi tilde I. Okay, so that happens if I set the standard, the winding derivatives to 0. Now I don't have to do that. I can keep also the tilde derivatives and set the standard derivatives to 0, or I can keep both. And it's indeed this perspective of keeping both that will allow us to understand what Q and R is. And so to illustrate this problem, let me now make precise what's the problem I want to address, and which we're going to solve in this context. Okay, so what's the problem I want to solve? So I explained to you roughly what double field theory is, and in particular, you can start writing it out in terms of the component fields, and if you set the extra derivative to 0, I told you just get back to the standard action. But suppose I don't do this. Suppose I keep all derivatives. Then the action will look as follows. So I told you there's an Einstein-Hilbert term. So I wrote it like this. Einstein-Hilbert term is the standard derivative with respect to the standard metric G. But if I keep all derivatives, there's also a second Einstein-Hilbert term now. And this one will be with respect to the inverse metric and with respect to the tilde coordinate. And it's the inverse metric because the T-duality rules would tell you that, or the Busher rules would tell you that G goes to G inverse if X goes to X tilde. So that works naturally here. And indeed, if you look back to what the tilde derivative is, that comes with an upper index. So the role of upper and lower indices is just consistently interchanged in the second Einstein-Hilbert term. And then there's all kinds of other bunch, and there's other stuff we want to understand. So,
I mean, the stuff that's going to be interactions between G and G inverse, right? I mean,
yes.
it's a very weird way.
Sorry?
All right. I would never would have written that. I mean, you know, you've
Well,
got,
actually,
you've got an Einstein-Hilbert term in some sense for the whole double field theory. And then writing as this.
yeah, that's true. So if you keep all symmetries manifest, you have one big Einstein-Hilbert
exactly.
term. But what I decide to do now, and that will turn out to be crucial, because if I want to talk about H, Q, and R, I have to go to components. I write it out in terms of the components and try to understand the geometry at the level of the components. And actually, there's an old paper by Zeitlin where he writes already this, almost exactly this equation, plus dot, 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 but he never worked out the dot, dot, dots. And sometimes what I'm doing now is to work out the dots. It's a very unconventional perspective, I agree, but let me just go on. So we have the standard Einstein-Hilbert term, and we know that one is, of course, diffeomorphism invariant under the standard diffeomorphism xi goes to xi minus psi I of x. And actually, xi can now be a function of x and x tilde, because in double field theory, everything depends on two coordinates. And similarly, the second term is invariant under dual diffeomorphism. So x tilde I goes to x tilde I minus psi tilde I of x and x tilde. But the standard Einstein-Hilbert term will not be invariant under the dual diffeomorphisms, because you see the parameter depends also on x, so the standard derivatives here will hit the parameter, it's not invariant. And similarly, the second Einstein-Hilbert term will not be invariant under the first diffeomorphism groups. So in double field theory, you have two diffeomorphism groups that are linked, and in the fully invariant formulation, covariant formulation that I haven't given you, it's clear that everything works out, but once you go to the components, you don't see the symmetry anymore. So all these extra terms, dot, 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 have to play a crucial role here. And the question is, can you set up a tensor calculus or geometrical formalism that allows you to make at least part of the gauge symmetry manifest? And the answer is yes, you can. Half of the gauge transformations actually can be made manifest. And depending on which field basis you use, that introduces this Q. So just for completeness, let me remind you that will play a role in a second, that for the standard Einstein-Hilbert term, we have the standard Christoffel symbols, which have an index structure like this, two indices down, one index up. And so that means in the dual picture, the Christoffel symbols, so in the tilde frame, we also have Christoffel symbols, which are standard. But since I changed now my convention of what up and down is, I get this Christoffel symbol with two indices up. And what I'm going to do now, and that's the operation that introduces the Q, is I will ask the question, given this expansion, and suppose I work now on this other field basis, so I can work on whichever field basis I like. I just use a different parametrization of the generalized metric. Working in this field basis, can I make the psi I transformations manifest for the full action? So the question is, can one make the standard diffeomorphisms psi I manifest for the full action? So in other words, what I have to do, looking to this term, because this one is already invariant, what I have to do is to have to covariantize the tilde derivatives, but not with respect to the diffeomorphisms of the tilde space, but with respect to the diffeomorphisms of the X space. So I'm doing now a funny operation, because I know already how I would covariantize it with respect to the standard diffeomorphism. That's just the standard Christoffel symbols. But now I'm doing something new. I introduce a covariant derivative that covariantizes the xi diffeomorphisms, if you like. So I have to invent a new type of geometry and new type of covariant derivatives, and as you will see in a second, that's what introduces the Q. Okay. Any questions so far? Good. So let me do that. So let me look to the double field theory gauge transformations.
Right, okay, I've got that. So why wouldn't you just start with double field theory, where everything's fine, and you know that you've got the diffeomorphisms of both x and x tilde taken care of, because you know that the action's invariant under those.
Yes, yes.
So, and I know what all the local symmetries are. They're given by generalized Lie derivatives.
Yes, yes.
And well, that's all done. So
yeah,
okay,
so it's
you
all.
may want to expand out the way that you're doing, because that's interesting. But then, what I'm sort of trying to understand is how active you are. You say you want to make, introduce a new covariant derivative, but surely that thing should be already in the double field theory, because you know that the double field theory is invariant under both x and x tilde diffeomorphisms.
Yes. But once you write it, the point is once you write it out in components, it's not manifestly invariant. And what I want to do is, at the level of component fields, I want to make it manifestly invariant. And it's because at the level of component fields that I can talk about objects like H, Q, and R, because they have little indices and not ODD indices. So it's just the motivation of talking about these non-geometric fluxes Q and R that for...
But
so
it is invariant. So
it
so
is
what
invariant.
you-
It's guaranteed to be
so now I'm
invariant.
worried you're
And
gonna-
I just want to make it manifest.
But now you're going to
So to
add
make it, just a minute, to make it manifest, are you changing the theory? You're adding
No.
new terms?
No,
or
I
you-
know the theory is already invariant.
Yeah.
It's just if I write it out instead of component fields,
Yes,
it's
yes.
totally obscured. And I want to rewrite this component expansion in a
Okay.
way that
It's
makes
not
the
changing.
gauge
No,
symmetry
I'm
manifest.
happy, yeah.
Okay, very good. So, so let me explain the psi gauge transformations. So on this tilde metric, it just transforms with the standard Lie derivative, not the generalized one, the standard one. And with the beta, this bivector introduced over there, it has a non-covariant term, or an inhomogeneous term, if you like, which looks as follows. So it involves the tilde derivative, and it is this invariant antisymmetric curl-like combination. And then there's also a covariant term with just the standard Lie derivative. And let me also use the notation where I introduce a delta, by which I just mean the full transformation minus the covariant part, the Lie derivative part. So that means that I would call this object here delta psi, because that's the non-covariant part, and G tilde has no non-covariant part. And the dilaton, of course, still transforms as a scalar. Okay, these are the transformations, and now I want to introduce derivatives that are covariant with respect to these transformations. So let's start with a scalar. So if we transform a scalar derivative, tilde derivative, you get the following. So just to remind you, if you take a scalar, take the standard partial derivative, you get a one form or covector, which is covariant, but now we're doing something else. We're taking the tilde derivative, which has index up, so that should transform as a vector. I think I will run out of time, so let me not go through all the details, but just inserting the transformation of a scalar, I get, of course, the following. And it turns out that I can rewrite this transformation using one of these constraints here, namely this one, the strong constraint, I can rewrite this as a covariant term. So that's just the Lie derivative of d tilde I, phi tilde, plus a term that is exactly this antisymmetric combination that we've seen in the transformation of the beta. So that's exactly equal to delta psi beta ik. So that tells us that the partial derivative, the tilde derivative of scalar does not transform as a vector, so it's not covariant, but its failure to transform covariantly is just by this beta term, so we can just absorb it by introducing a new derivative d tilde I, which is the d tilde I partial derivative minus beta ij dj. So that derivative will play an important role, and that implies then that the non-covariant variation of d tilde I phi tilde is 0. So that's done. The derivative of a scalar we can do. And I should stress that this derivative over there is not yet a covariant derivative. So even though its derivative on a scalar transforms covariantly, its derivative on higher tensors will not transform covariantly, and that's where we have to introduce a connection. So you should more think of this as some sort of unholonomic partial derivative, which is non-commuting, but nevertheless not yet a fully covariant derivative. Any question?
Why have you got beta to begin with? If you just did double field theory.
So I do double field theory in this field basis.
In that frame.
In that field basis. So from the point of view of double field theory, it doesn't matter how I parameterize the generalized metric. I can do it with a symmetric tensor and a bivector, or with a B field. And I decide to do it with the bivector. And again, that's because we're interested in these non-geometric, in this Q and R. Okay. So the scalar works, but now in order to have it work for a vector or a covector or general tensors, so that's the next case. Covector, we have to introduce now connections. So we introduce now a covariant derivative nabla tilde bj, which is this d tilde partial type derivative, but now there are extra terms involving a new connection, gamma ijk bk. So I put a check over it in order to distinguish it from the standard Christoffel symbols, and you may note already that it has the same index structure as these Christoffel symbols over here, which would covariantize the usual dual diffeomorphisms. And now for a vector with a lower index, it's the same story. And similarly for tensors with an arbitrary number of upper and lower indices. And now by requiring that this transforms covariantly, you can find out what should be the inhomogeneous or non-covariant part of the variation of the connection. And that turns out to be the following. So you get the following inhomogeneous transformation of a connection, or rather, requiring this, you can check that these covariant derivatives indeed transform covariantly. So that's now a new type of connection, which is different from the standard Christoffel connection or Christoffel symbol, in the sense that the index structure is different, but also the transformation behavior is now different. So you see, in the standard Christoffel symbols, you would have that the symmetric part actually transforms as a tensor, and that's why you can call it torsion. But now the symmetric part here has no special property. So that symmetric part is not separately tensor, the antisymmetric part is not separately a tensor, so you cannot set it to 0. So the whole story changes now, and that means that the final connection will have different properties, and what we have to do now is to determine it in terms of the physical field by imposing constraints. Okay, so we impose two constraints. One constraint is that the covariant derivative of the metric is 0. So that's the usual constraint, metricity, covariant constancy of the metric. And that does not determine now the connection completely, in contrast to the standard case, because there we would also impose the torsion constraint. That we can't do now, because the torsion, or what would be naively the torsion, is not a tensor. So in order to explain the second constraint, let me first note a property of this derivative over here, this d tilde, which I forgot to mention before. So I told you it's non-commuting, but I forgot to give you the commutator. So if you compute the commutator of this two derivatives, you get one term that involves the partial derivative, and you get one term that involves this new tilde derivative. So you get two coefficients, and I've called them already R and Q, because these are the objects which we later identify with R and Q. And in fact, these objects also, these expressions coincide with what people have proposed in the literature for Q and R flux. So here you see them emerging on the right-hand side. And another important feature, the property of these tensors is that the R appearing here is a tensor. See, the R is covariant, and that you can just check by an explicit computation. So that means the non-covariant variation of this R is 0, but the Q is not. The Q transforms in some funny way, and indeed it's not, there's no reason why that should be covariant, because these derivatives are not covariant.
Sorry, what's that R got to do with your other R? With your R that you began with?
Well, it's a proposal for what the R flux should be, but it happens to coincide with other people also propose or find.
No, but you've written in terms of something called beta. So, okay, you use the same label beta, and it's a bivector. But it's, I'm coming back to my confusion right from the very beginning of how do you know that by just doing this field redefinition at the beginning and then calling something beta?
Well, you don't have to call it field redefinition. Double field theory is just a different way of parameterizing things. You know, if you you can just evaluate the action in one parameterization or another one, and these are related by duality, if you like.
Yes,
and what people do in reduction is you say, okay, the standard reduction gives you the standard flux. Now in the internal space, you can do also go to the dual frame. That gives you the R, and that's what the R that people find is exactly this one. So from that point of view, it makes sense. It's a proposal, if you like. But there's no, you see, there's no rigorous proof you can do to prove that this is the actual R, because what's your definition to begin with? Yeah, you have to have an independent definition in order to say, I prove you now that this is the R. And there's no such a thing.
Well, okay. Maybe we should sort this out.
Okay. So that was just a side remark to justify now the second constraint. The second constraint is that the covariant derivative commute on a scalar into the R ijk, which is a fully covariant object. So the R is a covariant tensor, the numbers are of course covariant, so that's a covariant constraint. And now this covariant constraint tells you, that's the easiest to solve, that the antisymmetric part of this new connection gamma, check, is given by Q. So using this commutation relation for this new derivatives, in this computation, you see there is an R term, there's a Q term, and there's a connection term, but you can just cancel them by putting them equal. And so that determines the antisymmetric part of the connection as Q. So now we see Q naturally emerging as part of the connection. And it's not just artificially like a torsion tensor added or not added, which you can always do, but it's a part which is needed in order for this whole connection to transform as a connection. So this is not separately tensor character, but it's identified as the antisymmetric part of the connection. And so together with the first constraint, the full connection is then determined. You can write it out explicitly in terms of G tilde and beta. So that's done. So the connections are determined, and all what remains is to compute invariant curvatures in order to write on an action. So how do we do invariant curvatures? Well, we can compute the commutator of covariant derivatives on higher tensors. Let's say on a vector vk. So as before, this has a term involving the r, ijp nabla p vk. But now, since we're acting on an object with more indices, there's an extra term involving an r check, ijkl, which is a generalized Riemann tensor. So since the left-hand side is covariant, this is manifestly covariant, so this must be covariant too. So that defines a Riemann tensor. But the interesting thing is you can do now also something which you cannot do in the standard formalism, namely you can define a new type of torsion. So I told you before, what we usually call torsion does not have tensor character, but there's something new. Now, because if you consider this combination nabla I phi tilde, so you can construct this new covariant derivative, this is the standard covariant derivative, which we always have. And this happens to be nabla tilde I phi tilde. And now in the same way that the commutativity of partial derivatives drops out here and gives you a tensor, in the same way is the strong constraint implying in this equation that the second derivative drops out, and this reduces to a first derivative times some calligraphic t multiplying the whole thing. And since this is a covariant equation, that must be a covariant tensor too. And so there's a new type of covariant tensor. That's what we call we can call new torsion, and it's just a trace part of the connection. So you trace the connection over the first index, and this happens to have tensor character separately. So that's the analog of what we usually take the antisymmetric part of the Christoffel symbols. That has tensor character, so we can call it a torsion. And here this is not true. The antisymmetric part does not have tensor character, but the trace part has. Okay, so now we can also, of course, define a Ricci tensor in the usual way. So we can define our check ij, where you just trace this new type of tensor over one index, and then we can also define a scalar, where you just trace in the usual way the Ricci scalar, the Ricci tensor. So these are now all the ingredients I need in order to write the double field theory action in terms of these geometric quantities, in which every term will be separately or manifestly invariant. So I'm almost done. So that's the double field theory action, which I wrote schematically over here. Two Einstein-Hilbert terms with respect to the standard and with the tilde derivatives. And this is now the exact form of the schematic form. So it's an integral dx tilde. So we have the standard Einstein-Hilbert term, R. That's the usual one, with respect to G tilde in this case. And now I can add the second one, which is a full R check. What I call R check here involves now this new connection. It involves the gamma check, which in turn involves the Q, but it also involves the standard Christoffel or the naive Christoffel symbol we would usually impose. And now there's a new kinetic term for this R flux, Rijk, which was defined over here. And then there's still the kinetic term for the dilaton. But since we keep all derivatives, you get also a kinetic term for the phi tilde. And interestingly enough, it happens that this comes in a combination with this new torsion Ti squared. So that's the final result. That's the double field theory action in these tilde variables, G tilde and beta. and is written in such a way using this novel type of geometrical formalism that makes the psi-I diffeomorphism symmetry manifest. It does not make the other half, the second diffeomorphism group, manifest. That's now obscure, but you could go back to the original field basis and make the other one manifest. So you can think of it as an alternative way of proving the gauge invariance of double field theory. And the interesting point is now that the Q squared terms, which I've shown you initially, coming from this brute force field redefinition of 10-dimensional supergravity, now just comes here from the gamma squared terms inside the Ricci scalar. So there's all kinds of terms, in particular this Q squared, and they are now reorganized in a very nice way into just one geometrical term. Okay, let me stop here. Thank you very much.
Questions?
So, if I look at the duality invariant string, if I look at, say, Chris Hole's doubled string,
Yes.
now I sort of have, it's not completely fresh in my mind, but if I want to include these sorts of fluxes in that, I thought the thing there was, and this was work with Ron Reed-Edwards, that you extend the duality symmetric string, you add some extra structure, some structure constants, some Wess-Zumino term, and these structure constants, I like the structure constants of some Drimfeld double, and you decompose it and you can pick out Q's, H's, R's, and F's from that. Why is that story not appearing in any of this discussion? I was expecting to see that sort of relating here. Like there you have to introduce something more than just the normal double field theory.
Yeah, I must say I'm not very familiar with that construction, so I'm not exactly sure what you mean by getting extra Q's and R's. Yeah.
Okay, well, we'll discuss it later.
Yeah, let's discuss
I'm
it.
just surprised that you don't need to add in something else on top of just normal double field theory.
Well, I should say, which I want to stress at the beginning, maybe I didn't say it quite enough. So what we've done here, of course, is just a rewriting of double field theory, or you can say, from the point of view of 10-dimensional supergravity, it's just a field redefinition. And so that means that if you now do a reduction of these theories, you get gauge supergravities in lower dimensions, which are at the end of the day equivalent to other gauge supergravities that you can get by standard reductions. You might, of course, still hope that certain solutions, which are very complicated and obscure in one frame, become easy and simple in another frame, so it may be still practically useful. But at the end of the day, you don't get all gauge supergravities that are known to exist in 4 dimensions from double field theory. So that would indeed require an extension of double field theory. And that's what people have seen already, that if you want to check, do you get the most general gauge supergravity, let's say for n equal 4 in 4 dimensions, you have to relax the Stone constraint slightly. And indeed, there are examples where you can see that you can relax it a little bit. So that's something still to be explored. It's very mysterious how to do it exactly to relax that constraint, but that needs to be done if you want to get the most general gauge supergravities. The hope would, of course, still be that these structures which you identify in the standard case sort of give you a guide of how to think about these objects in the most general case, if that turns out to be possible.
Any other questions? One more. So I mean, I would have thought, you see, I mean, I guess it's like Dan says, I would have thought, see, everything you've done is local, right? I mean, you've done a field redefinition, you pull some things out, everything's about local stuff. But you see, if you go back to your original set of arrows that you had between F, Q, and R and all that stuff, I mean, really those fluxes are about non-local data. So, I've got an H thing, then that's something in the cohomology. I then got something which is the twisted torus. And so it's the fact, which is the thing which you called F, right? When I take the dual of something with H flux. And the twisted torus, it's all about the fact I have a global twist in the SL2 group as a phi ration over some S1. And so it's a measurement of an obstruction topologically from going around some cycle. And then when I do the T-duality of that thing, you know that you get a T-fold, and really F is measuring T-fold flux. And then again, that's global data in terms of having an ODD thing that where you go around some non-contractible loop, and I come back up to an ODD transformation, and then indeed those things ought to be geometric as fluxes in this thing. So what's confused me, and from the very beginning, is you're doing a whole bunch of stuff which is locally always equivalent. You just do some field redefinitions, and yet the fluxes that we're talking about, which is measuring things like twisted torus twists or T-folds, etc., which is what the Q thing ought to be related to, seem to be all about global data, right? It's about global stuff. It's about taking stuff around some cycling.
But you see, like if you talk about, for instance, the geometric flux, you say that tells it already comes from some non-local issues, the F. But at the end of the day, that's a standard local expression, and we know exactly what its geometric role is in the conventional action. It's just related to the Levi-Civita.
Yeah, but that's
connection.
the point. I mean,
so
okay, go on.
and so why should you not be able to write down an action for Q and R?
But you see, my point is that if we take H, for example, where we have H flux and we've got something in the third cohomology on a torus, you're writing it down in terms of the normal field. You don't introduce a new flux because I've got some new non-trivial vibration. And so when I've got Q, in terms of double field theory, that should be expressible in terms of all the fields in the double field theory, because it's just as I go around a cycle, I come back up to ODD transformation. That's a T-fold.
Yes.
So I should be able to write down stuff that is Q flux just in terms of G and B. Now, I'm not saying you're wrong, but what's confused me is that what makes the thing flux is a topological thing. It's you're starting with something topological, which is basically your U1 bundle on a torus, and then you do these T drives into something which is an ODD.
So maybe that's
global thing.
So maybe
that's you're measuring that charge, and then you're right. It shifts between B field, it goes into geometry, and then it goes into ODD-ness. But at no point I go, oh right, I've got to introduce new fields.
Well, actually, maybe that's a good point. Maybe that's related to this issue I mentioned at the beginning, related to your question, that this decomposition of the generalized metric in terms of G and B is actually not always well defined, in the sense that if you apply a T-duality transformation, you may map it to a situation where you cannot read off a non-singular G, but even though the generalized metric by itself is still well defined. And so the transformation or the field definition we've been doing here is actually of the type. So you do a T-duality transformation that in general, I don't know if it's always well defined. So it's of course by itself is always well defined, but it may run through some field configuration which is not well defined anymore. I haven't thought about this very much, but in general that's the case, that the fundamental formulation of double field theory uses a generalized metric that is always well defined and has a well defined ODD transformation. But the moment you write down a particular parametrization, it's not so clear anymore. And it's what we have been doing here in some sense is writing down the double field theory action in the parametrization, which is the transformed one from the standard one, where you go through this T-duality inversion. So that might be related to this issue.
Yeah, I mean, I think I'm going to say the same thing. I mean, if you started out not with a metric, but with a verbine in doubled space, then normally you make an OD choice to go into upper triangular form.
Yes.
And then that will give you B. If you do the opposite, then you'll get something opposite. So if you were, but then this comes back to my point, which is, there's a choice there whether you're upper or lower triangular in the verbine. But normally we go, it doesn't matter, right, which one it is. That's the whole point. Everything should be variant. But we allow ourselves some global obstruction to picking that thing. And that's what really these fluxes are. So I agree with you that it's related to that parameterization, but I'm still confused that I'm somewhere in the depth of my soul, I think this has to be global data, not local stuff. Because otherwise, if it was all local stuff, right, then you can't have new local stuff floating about.
Maybe another way to ask David's question is if you take one of these gauged supergravities dualities that you cannot get by usual dimensional reduction, but you
Yes.
tell us you can get it this way.
Well, I told you it's what this construction does. It gives you those gauge supergravities that are related to those that you can get by standard reduction by a T-duality or by an 066 transformation, let's say. So it completes the T-duality, the orbits, exactly.
But so if I take one of these theories and I try to write down the backgrounds that give me what I want, can I work backwards and see what kind of backgrounds in the original standard action I would have to turn on to go there? Or at some point you lose, I guess, the thing because you have to introduce X tilde dependence. Is this the
Yeah, that's true. If you do a T-duality transformation, X dependence becomes X tilde dependence.
You should still have section condition.
But yeah, there's always a section condition. But I'm not sure if that's the issue, because you can always rename X tilde into X, and that's just at that level a matter of convention. So I agree that in principle you can always go back. So that's what I try to
can
indicate
go back,
with
why
this.
not try down directly, these new gauged supergravities with the old action? I mean, why do we
Well,
have
the
to
gauge
write down
supergravities you can write down directly anyhow. So that's if you're just
I
interested.
thought you
in-
said not all of them. No,
you can,
I'm sorry.
but-
I want to write down the 10-dimensional backgrounds
Yes.
of the conventional theory, without doing this. That would give me these new gauge supergravities. Let's call them new. They are not new, right?
Yeah, they're not really new, but
Sorry. Someone is objecting.
uh,
My question. Yeah.
um,
So they are not new, but they are related through ODD.
yes. So
So
no, what's not exactly the question?
why can't you write down 10-dimensional backgrounds that will give you directly these new gauge supergravities?
Well, in these new variables, you can do that.
Yeah, but then I cannot work backwards. I mean,
Do the field redefinition back and write it in terms of the
Yeah.
original metric and everything
Yes,
else.
yes.
you cannot do this.
No,
Presumably,
in
because if you
principle,
could,
no, I mean, unless there's an issue of the type we were just
But I think
discussing.
that's probably the point, right?
You
I bet
can
when you
go
do it
up.
in the original variables, you'll find that it was a t-fold. And that was why you never spotted it before, because you were just looking for dimensional reduction under ordinary manifolds.
it's only a t-fold, it's probably not too bad, but
Yeah.
it's probably some sort of very singular.
Or something like that. That's probably why they're missing, right? I mean, it's the same with an H-flux. You imagine doing an H-flux and it's fine, and then you get something in supergravity, and then we know in the T-duality that goes over to a T-fold. So there must be some gauge supergravity that's living there. That's that T-fold. Good. And this demonstrates that the chairman should never be interested in the talk. Okay, thank you very much.